Hello, my name is Ashok Krishnan. I'm from the Indian Institute of Science, and today I'll be presenting our work titled Optimal Pricing in Finite Server Systems. So our work is basically concerned with pricing of servers. If you have a server farm, how will you price the servers optimally? To illustrate the problem that we're considering, let's consider an example. Consider a case where there are 5 servers available with a firm, of which 2 are busy with some job, and then a new job arrives. And the job has an associated value to the customer who is bringing the job. This value is represented as V. What this means is that this is the maximum price that this customer is willing to pay for the execution of this job. Now, the server proposes a price, the server farm proposes a price so that the customer can pay this price and enter the server farm. This price is denoted P2 because the price would of course be a function of the number of busy servers. The more servers being busy means a resource crunch on the server system. So you expect the price to be proportional in some way to the number of busy servers. Now that a new job has come, now the customer has 2 options. One is that if this price is too high, that is, if P is greater than the value that it associates, the customer will leave the queue without joining. However, if the price is small enough, that is, V is greater than P2, P2 being the price that is asked, the customer will join the system and you have 3 busy servers now with the new customer in the system. Now, any new customer that comes in at this point will be asked a price which is proportional to the current number of busy servers, which is 3. So the system evolves in time like this. Now, the question from the point of view of the server farm is how to choose these prices, P0, P1, etc., so as to maximize the revenue. Now, this is a problem that has been considered in the pricing literature for some time. There have been a number of works that looked at this along different angles. Now, one angle that has been there since the beginning of the pricing literature is a question of social optimization, where you look at some kind of a social utility function and you try to maximize it. What we have just described is called revenue maximization, which is the question from the perspective of the firm. So these are some works that looked at it. Now is the earliest work in the pricing literature for the queuing case. There have been works that looked at homogeneous customers, work that looked at heterogeneous customers. Homogeneous customer would mean that all customers have the same value associated with the job, a fixed quantity. Whereas heterogeneous customers would be a set of customers who draw their value from some distribution, let's say. So these are some examples of works which have heterogeneous customers. And there have been works that have had works that looked at single server kind of scenarios, multi-server scenarios, processor sharing scenarios. Most papers in this literature fall in the intersection of these axes. So you'll find papers, for example, that look at social optimization in a setup with heterogeneous customers and multiple servers. So you can imagine all kinds of combinations. So where our paper situates itself is that we're looking at the revenue maximization problem with heterogeneous customers and a multi-server system. So in some sense, this is a generalization of the results in this paper. And we get results that kind of re-establish some of their results, as well as we get new results. So the system model we have is this. We have arrivals coming as a Poisson process at rate lambda. And each of these arrivals has a value function V, which takes values from a distribution G. So G is the CDF. Now there are 5 servers in this example, and now once a job enters a server, it stays there for an exponential duration of time with parameter mu. So this is a Markovian system, and you can construct states and state evolution. So the state where all the servers are free is called state 0. If exactly one server is busy, it's called state 1. So then you can have state 2, state 3, and so on. And when do the state transitions happen? For example, if your servers are in state 1 and there's an arrival, this arrival has a value V. If V is greater than the price that is on offer, the price is P1, then the transition happens and the system moves to state 2. In the other direction, when does transition happen from state 2 to state 1? When either of the two working servers completes service. So one job leaves the system and we go back to state 1. Since these two servers are working at exponential mu rates, this reverse direction transition will happen at exponential as an exponential 2 mu variable. So this is a compact representation of the state transition. You are in state 1, you move to state 2 at the rate lambda times the probability that the value exceeds the price in this state. Similarly, you move from state 2 to state 1 at rate 2 mu. So overall, the state transition for a 5-server system can be represented like this. These lambda i's are just compact notations for lambda times the probability value exceeding the price in that state. So we use this G bar to denote the complementary CDF corresponding to the value function. Now, once you have this these balance equations, you can solve them to obtain the stationary distribution pi of the system. And once you have pi, because the arrivals are Poisson, it follows that if there are I busy servers, so an arrival sees I busy servers with probability pi I in stationarity. And in when the state is I, the price is pi. Therefore, the revenue that can be extracted in state I is pi I times the probability that the arrival joins the queue, which is G bar pi, times the price itself. And when you add this up over all the states, you get the total revenue of the system. So this is the revenue that we seek to maximize. Now, this is a complex function for many reasons, because one primary reason is that pi i's are rather complicated expressions of pi. And this is a multivariate function that we have to optimize. So getting intuition about this is not very easy, nor does it follow easily analytically. So for getting some understanding of some easily tractable policies, we consider first an extended kind of scenario in which you have infinite servers. When you have infinite servers and you write the revenue expression, it turns out to be the same expression, except that we have infinite servers. And now, instead of G bar pi, if one replaces that by the value of this function at its optimal point, note that this summation becomes 1. So what follows from this equation is that in the infinite server case, the optimal price is this price, and it's the same price that you have to charge for every server. So in the case of having infinite servers, the optimal pricing is not differential, it is uniform across servers. And this makes sense because when you have infinite servers, you always have an infinite number of free servers in your hand, whatever is your state. So state dependent pricing does not make sense, and what makes sense is uniform pricing. So this is an extreme scenario, but what happens when you have finite servers? For finite servers, we also construct a suboptimal scheme. So consider a case where there are finite servers and you assume that all states have the same price. Now, these prices are a subclass of the total possible pricing schemes. Now, if you find that price in this subclass, which is optimal, that's called the uniform price for the system. So in the 5-server case, you can see that you can write that expression like this. So this is one suboptimal class of prices, which we'll use for comparison. The actual optimal price looks like this for a 5-server system. These blue bars show those prices. You can see that they're increasing. Further, for comparison, we have drawn the level of the uniform optimal price, which is P5 star. So the actual optimal price is higher than P5 star. So this is the price when the system has 0 busy servers, when the system has 1 busy server, and so on. And these prices are here. Now, these prices also have some very interesting analytical properties, which you have shown in the paper. These properties are like, while we are demonstrating, we're using figures, but in our work, we actually show them analytically. Some of these are very intuitive properties. For instance, observe that revenue is increasing as arrival rate is increasing. This is, of course, to be expected. However, the revenue per arrival rate decreases, which means your marginal return per customer is kind of reducing. Again, not surprisingly, revenue increases as service rate increases. So service rate is kind of your installed capacity in the system. More capacity you have, more revenue you get. So this is not surprising. But what's surprising again is that revenue per service rate is decreasing. So per resource, the returns you get in terms of revenue actually decreases as you increase your resources. In a similar vein, revenue increases as the number of servers increases, whereas the revenue per server actually decreases. So all these are not results that we show by simulation, but these follow from the actual expression of the optimal price, properties of the optimal price. Further, we also show this kind of a nice monotonic property. You have these prices. These are, so the first three components of the price. So this is the case of 3 servers. When you have 3 servers, the price is 3 components, right? P0, P1, P2, let's call them. And when you have 4 servers, you have 4 components. However, we plot just the first 3 components of every price for 4 servers, price for 5 servers, and so on. Now, if you just compare the first component, the green bars, you can see that they're monotonically decreasing. If you just look at the red bars, again, you see they're monotonically decreasing, and the blue bars also are monotonically decreasing. What this means is that the optimal prices are component-wise decreasing. We show this property analytically. And you can also see, and this holds for all components, though for representation, we have only used 3 components, but it's true for all components. And further, you can see that the prices, the difference between the first price and the second price, P0 and P1 and P1 and P2, these differences are huge when you have 3 servers, but the differences kind of flatten out when you come to 7 servers. What this means is that in the 7 server case, you're coming closer and closer to the infinite server kind of situation, and therefore you would come closer to uniform pricing, and this P star represents the uniform infinite price that we talked about earlier. So the prices will actually decrease. You can see the trend here, and they're decreasing, and they're kind of converging to this P star value. And further, you can also see how the revenue can be compared between optimal prices and uniform prices. So here we are comparing 3 prices. On the first, we have P star, which is the infinite server price being used for all servers. This is for a system with 5 servers. So we use the infinite price for all servers here. P5 star is the optimal uniform price, that heuristic that we defined earlier. And P underline, which is the green bar, represents the actual optimal price. Now you can see that the actual optimal price is always better than the other 3 prices, and this improvement is pronounced in the case where the load is high. And remember that load is arrival rate divided by service rate. So as you push your system towards higher load, towards a resource starved scenario, what happens is that you get more and more benefit out of non-uniform pricing. So uniform pricing kind of works okay when you have low loads, and as a heuristic it's good, and even performance wise it kind of matches with the optimal pricing. But as you increase the system load, uniform pricing is no longer very good. So you would expect some sort of result like this, because in heavy traffic, certain states like heavily loaded states are more common, and the probability gets skewed in that direction. So you might expect something like this as well. So in summary, what we have done is the following. We have done the analysis, the theoretical analysis of a system with heterogeneous customers taking values from a distribution. We have solved the server pricing problem for revenue maximization. We also observed that uniform pricing is optimal for infinite server systems. However, for finite server systems, it's not optimal. We obtained an analytical solution to the maximum the optimal maximum pricing for a finite server system. And this is generally, so often in MDP, you don't get analytical results unless it's for very particular simple systems. However, in this rather general case, we are able to obtain a tractable analytical solution by solving a fixed point equation. And further, we also develop two simple heuristic algorithms of pricing a finite server system. One we get from the uniform price and one we get from the infinite price. We study the properties of optimal pricing and we observe some very interesting trends in the revenue and the price, how the price varies, how the revenue varies as we vary certain parameters of the system. Furthermore, we have also done performance comparison between the optimal and heuristic algorithms for finite server systems. And we observed that for heavily loaded cases, using uniform pricing is at a disadvantage and the optimal pricing has an advantage. However, at low loads, you can use uniform pricing and get away with it. So this is a summary and that's the takeaway. Thank you very much.